Welcome back to the discussion on factor groups. In the last class, we studied that if phi is a homomorphism from G to G dash, where G and G dash are two groups, and if H is a kernel of the homomorphism, then the coset multiplication AH into BH equal to ABH is well defined, and there exists the factor group G over H, which is the set of all cosets of H in G. And while proving this result, we used the property of the kernel of phi that the kernel of any homomorphism is a normal subgroup of the group. Therefore, here H is a normal subgroup of G, and using that property of H, we showed that this operation is well defined and this factor group G over H exists. Now, in this theorem, we are going to show that if H is a subgroup of a group G, then the left coset multiplication AH into BH equal to ABH is well defined if and only if H is a normal subgroup of G. So actually our former result was only a corollary to this theorem. Now let us prove the theorem. First of all, let us prove the necessary part. Let H be a subgroup of G, and suppose the left coset multiplication AH into BH equal to ABH is well defined. We have to show that H is a normal subgroup of G. That is, we have to show that AH equal to HA for all A belong to G. Now, what do you mean by the statement the left coset multiplication AH into BH equal to ABH is well defined? The coset AH is the notation used for the coset of H in G containing the element small e. And if you take other element X belongs to the same coset, then this coset may be given the notation XH also. Suppose we are taking the element X from AH and I am taking an element Y from BH. Then the coset AH is equal to the coset XH and the coset BH is equal to the coset YH. And if we multiply these two cosets, actually we can write the answer as XYH. Here the operation is well defined means that if you multiply these two cosets, then ABH is equal to XYH. That is, if you take any element from the coset AH and you take any element from the coset BH, then the product becomes an element in ABH. That is what you meant by the operation is well defined. Now let us prove the statement that H is a normal subgroup of G. To prove the result, we will show that AH is a subset of HA and HA is a subset of AH. That is, inclusion holds for both directions. First of all, we will show that AH is a subset of HA. For that, we will take an element X belongs to AH. We have to show that X belongs to HA. Now, we are going to consider two cosets here. One of the coset is AH and other coset is A inverse H. And I am going to take the representatives of each of these cosets. From AH, I am going to take the element X. And from A inverse H, I know one of the elements is A inverse, so I choose the element A inverse. So choose the element X belongs to AH and A inverse belongs to A inverse H. Since X belongs to AH, the coset XH is equivalent to the coset AH. Now let us multiply these two cosets together, XH into A inverse H. This is equal to X A inverse H. Since the operation is given here as AH into BH equal to ABH. Now let us choose other representatives for these cosets. From AH I am going to take the element A, and from A inverse H I am going to take the element A inverse itself. That is, we are choosing the element A belongs to AH and A inverse belongs to A inverse H. Again let us do the multiplication here. That is, we multiply AH into A inverse H. This is equal to A inverse H. And A into A inverse is actually the identity element E. So this is EH and EH is actually equal to H. Here we are operating the identity element E with each of the elements of H. Then we will get the elements of H itself. So EH equal to H itself. Here what happens is that we take the element X belongs to AH here. That is, XH is equivalent to AH. And here we take the element A inverse belong to A inverse H. Therefore, if we multiply these two cosets, XH into A inverse H, actually we are multiplying the cosets AH into A inverse H. And here we do the same AH into A inverse H. Here we get the answer as H. But here we get the answer as XA inverse H. Since the operation is well defined, this XA inverse H should be equal to H itself. This means that the coset containing XA inverse equal to the coset H. In other words, XA inverse is an element in the coset H. This implies that there exists an element small h belong to capital H such that XA inverse equal to H. If we multiply both sides with A, we will get X into A inverse into A equal to HA, or I can write X equal to HA. This means that X belongs to capital HA. The X belongs to the coset HA. So we start with an element X belongs to AH and we showed that X belongs to HA. That means that AH, the coset, left coset AH is a subset of the right coset HA. With a similar argument, you can show that HA is a subset of AH also. So this means that AH and HA are exactly equal cosets. Or in other words, the left coset AH is equal to the right coset HA. Therefore, H is a normal subgroup of G. Thus we showed that the left coset multiplication is well defined, then H is a normal subgroup of G. Now we have to prove the sufficient part, that is, we will assume that H is a normal subgroup of G and we will show that the coset multiplication is well defined. Now assume that H is a normal subgroup of G, we have to show that left coset multiplication AH into BH equal to ABH is well defined. I had explained the same result in the case if H equal to kernel of a homomorphism from G to some group G dash. We are performing the same proof here also. To show that this operation is well defined, I have to take one element from AH and one element from BH and we will show that the product of these two elements always belongs to the coset ABH. No, so let the element AH1 belongs to AH, the coset AH, and BH2 belongs to the coset BH. We will show that the product of the elements AH1 into BH2 belongs to the coset ABH. So consider AH1 into BH2. Now we consider the element H1B. Actually this belongs to HB. Since H is a normal subgroup, HB equal to BH. Therefore we can see that the element H1B belongs to BH. This implies there exists some H3 belongs to capital H such that H1B equal to BH3. Therefore, we can rearrange these terms here. AH1 into BH2 can be written as A into H1B into H2. So, this is equal to A into H1B is BH3 into H2. This can be written as AB into H1 H2. Here the element H1 is 2 belongs to capital H. So, we can say that this element AH1 into BH1 belongs to ABH. So, if we take any element AH1 belongs to AH and any element BH2 belongs to BH, we showed that the product always belongs to ABH. That means that the left coset multiplication is well defined here. Hence, we showed that the left coset multiplication AH into BH equal to ABH is well defined if and only if H is a normal subgroup of G. As a corollary to the theorem, you can show that if H is a normal subgroup of G, then the cosets of H in G form a group G over H, which is the factor group with a binary operation AH into BH equal to ABH. In the theorem, we showed that this operation AH into BH equal to ABH is well defined. To prove the corollary, it is enough to prove the group conditions. First of all, we have to show that the operation is associative. So we will take three cosets AH, BH and CH. Now we will consider AH into BH into CH. So this can be written as AH into BCH by the operation defined here, which is equal to ABCH. Similarly, if you do AH into BH first, then we will get ABH into CH gives ABCH. So clearly the operation is here associative. Now what will be the identity element of this factor group? Clearly it is H. Since H is equal to the coset EH. So if we multiply EH with any other coset AH, we will get EAH, which is equal to AH. Similarly, if you do AH into EH, then also we will get AH. Therefore here EH is the identity element of this factor group, where EH is equal to the group H itself. Now we are to show that every element in G over H has inverse which belongs to the group itself. So we will take a coset AH belongs to G over H. Since AH belongs to G over H, the element A belongs to G. So there exists an element A inverse belong to G since G is a group. So we can consider the coset A inverse H. And what will be A inverse H into AH? This will be equal to A inverse AH, which is equal to EH, which is the identity element of the group. Similarly, if you do AH into A inverse H, then also we will get the identity element H. So clearly, the inverse of the coset AH is A inverse H. Hence we showed that with this operation AH into BH equal to ABH, the set of all cosets of H in G, which is represented by G over H, is a group which is called the factor group. To have a clear idea about these concepts, in the next class we will do some problems such as find the order of a given factor group or find the order of some elements of a given factor group. Now let us stop here.